will do their best, it is the responsibility of the application to allocate free memory in a manner which doesn't mess with the allocator's mind, really.
Clive, can you explain the realloc issue with libumem?
Okay.
I believe we saw something funny with realloc in UMem years ago. Yeah.
So, can I remember what the behaviour is? There are different behaviours between libc and libumem. I'm struggling to remember what they are. If it comes back to me, I'll let you know. Right. Or if you're interested, I can go offline. So, how are we doing time-wise?
25 minutes.
25 minutes, okay. So, next bit, we have processors, T4, in this case. And how do we look at what's going on inside to see, how can we understand the behaviour of the chip from a performance point of view? So, one of the, and this has been in Solaris since at least 2.6, is the concept of large pages. So for Spark, we've got 8K pages as default page size. For x86, we've got 4K pages. In this case, this is Spark. And when we do when an application accesses a piece of memory, there'll be a translation from the virtual memory address to the physical memory address. And if you have, let's say, an Oracle, 100 gigabyte Oracle system global area, that's an awful lot of 8K translations. And since these are, there's a limited amount of space on chip that can be allocated to these translations. So what is done is we use there's a range of page sizes. I think 1 gig is the largest I've seen. Sorry, 2 gig is the largest page size I've seen in some of the modern Spark machines. But 4 megabytes, the traditional that's traditionally used. So instead of having to do a large number of 512 8K translations, we can do one, and that is going to be a lot quicker. And this can even show dramatic improvements. So I think it was Solaris 10 Update 2. The stack and heap of processes went from 8K by default to 4 meg, or 2 meg. And this, again, is resulted in a performance gain. So how do we know when we should do this or start looking at this? And this is TrackStat, and in this case we're using -T flag. And what we can see here is that data TLB misses are taking up 46% of the machine. And that should be a trigger for us to say, okay, let's go and look at the applications that are running on this machine using a lot of CPU time. Perhaps they're the ones taking data faults in PRStat. And do we have any scope for using large pages? So perhaps, there can be causes that Oracle, for some reason, isn't set up properly. There's also a PPGSZ, which allows you to set a page size for an application. So in this case, we could potentially be running 2 times faster using large pages. This is a really easy win. So going down a little bit further, does anybody go to Solaris 8 services seminars? Back in about 1998, I think, 1999. I ended up talking about performance instrumentation counters, where you have tools, CPU stat, CPU track and bus stat, which allow you to look at events like instructions, E-cache misses, D-cache misses, instruction cache misses, fills and spills. So CPU stat would allow you to look at the entire system, CPU track on a per process basis. And these are described in the generic events. Mature technology, something we use internally in both processor development and operating system development. And if you want to find out what the platform-specific events are, we can use CPU stat minus H. So as an example, so that was Solaris 8. For Solaris 11, for those who may know John Haslam, he had the bright idea of bringing dtrace and the performance instrumentation counters together so that you can use the functionality of dtrace to, for example, say, well, actually, I want to know what application, I want to know what function stack is generating E-cache misses, and to bring those together. And after a lot of head scratching, he came up with the CPC provider for dtrace. So this is a very small example down here, where we look for level 2 cache misses. Now, there are two ways you can describe the performance instrumentation counters. There are as many types of machine, so each type of machine will have a different description for many of the counters. So for example, things like instructions will have a different description or a different tag for different versions of Spark, for different versions of x86, AMD, Intel. Or we can use what's described as PAPI, which is a North American university, put together a set of descriptions. So if you wanted to look at PAPI L2 decache miss all, and sample it every 10,000th of a second, then you can use that terminology. And it doesn't matter what machine you're on. Or you can go and read the programmer's reference manual for the architecture you're on and go and work it out. I'll choose the PAPI route, actually. It makes it an awful lot easier. So if we wanted to work out on an application, maybe what was, for HTTP, what was the function that was creating data cache misses, we could use that. And I sort of bring this up because I think it's one of the untapped performance opportunities that is really not being used to the full. There's a bit of sort of, a bit scared to dig down that low. So here's just some examples of you can either for a PAPI data for a level 2 data cache read, we can either say PAPI L2 DCR, or for this type of AMD processor, we can do a DC plus refill from L2 for an Intel Pentium Pro L2 load, and actually that isn't relevant to those Spark processors. They don't have that concept. I'm just trying to demonstrate here is you really don't want to do the platform-specific stuff. So cycles, how many people have come across or used cycles per instruction? No, come across it? Ooh, okay. So in the HPC world, this is quite significant. I did some work when this was still in kind of a prototype with a university who's trying to do quite a trivial operation of trying to model the start of the universe. And we managed to get about a 20% improvement through using an early version of the dtrace CPC provider. And what we found is that there was a Fortran array, and I can't speak Fortran, was overflowing the cache line. So they resized that, and they got about 20%. And for them, 20%, and their jobs can take months to run, was worth another paper in Nature, which is really important to them. And for calculating the cycles per instruction, we can either do PAPI total cycle cache, or PAPI total is divided by PAPI total instructions, or we can go and work it out for each of the different processors, and we'll get there's just this little bit of awk at the end of this CPU stat line. We can get out the cycles per instruction. Okay, so how does that help us? Well, it tells us, and I've used this a few times, how, if you're in sales, maybe this is not the thing, new hardware, always a solution. It tells us where we might get some advantage with an existing application. Where should we go in trying to make that faster? Is buying faster or more CPUs the right way to go? So if the cycles per instruction is low, we examine the application for unnecessary work, maybe get faster CPUs, or possibly more CPUs if the application scales. If the CPI is high, so there are lots of cycles, we're waiting basically on memory latency bound, we might examine the application for unnecessary memory work, perhaps with some optimizations with an Oracle C compiler. Seen this less, but one of the easy wins used to be customers compiling with GCC, and then just put the Sun Studio, the Studio compilers, and minus fast, 2x is yours, and that was kind of quite pervasive. That sort of easy stuff's gone. Sometimes improve with processor sets might improve memory locality. That's not worked for me. CPUs with larger caches, and maybe test a different CPU architecture. So there have been a few occasions where some of the T-series, because the various cores share a cache, that can work really well. So CPI might actually guide us in a direction as to where we spend our money. Questions? Comments? Thoughts?
Where do we learn all this information? Yeah. I mean, your slides say, oh yeah, I'm dreaded user of the IO stuff command later tomorrow's work, just dreaded worried about my disk, but it's always good to see that, but when it comes to real life, it's where do I go? I mean,
isn't that
manuals,
Oracle
books.
Advanced Customer Services? So we can help you. Yeah. I mean, I think there's a couple of. I don't know. Where do you learn it? I don't know. It's.
The Wikipedia page.
Yes. It comes to events like this. My colleague Jared Nash will be wonderful. Do come next time. I don't know where you learn this, and I think, in a way, going back to the title of the talk about good practice, is kind of, what do we bring? Well, it's kind of, we go and look at other people's disasters. Because, I don't meet many customers. It's nice coming here. Nobody's shouting at us. Nobody's irate. Everyone's had biscuits and tea. Yeah. So, but I guess I don't know what the answer is to that, and it's interesting because I do some talks for there's a thing called Technicamps, which is about introducing school children to technology. And I was asked the same question by a 13-year-old, how do you get to know what you know? And, well, I don't know. And how do you get to know this stuff? I don't know, you kind of go and do. Sorry, I haven't got a better answer. And I'm really open to, I believe that customers have very good judgment. Most customers have very good judgment. You're more than welcome to email me if you've got a question or I think 10 minutes or 15 minutes chat is always free. So Clive.King, it's not that difficult to find my mobile number on the internet. If you phone me at 6 o'clock in the morning, you will get a small boy who will talk about Star Wars. If you phone me at 3 o'clock in the morning, you will talk to the dog. But I'm absolutely open to, if you want to know where to go with this, and if it should, sometimes we're seen as maybe being less helpful, but for certain circumstances that they need to get